Okay, right. So let's begin. Right. So today, this chalk's a bit scratchy. Let's see. So I'm going to use. You're going to have to remember some of the stuff we've already done today. So, but hopefully it'll help remind you of stuff we did last, like a few weeks ago. Okay. I just don't like it when the chalk scratches and squeaks. Right. So last time I sort of introduced what happens in 4 dimensions compared to 10 dimensions, and in 4 dimensions we still had sine mu on the holomorphic side, but now it was only in 2 transverse directions. So mu is 1 and 2, say, and then we had so a result of like going from 10D to 4D, you get 6 compact components of the spinner, like the sine. So this used to be 8 degrees of freedom because it was 8 transverse directions in 10 dimensions. So now you've got 2 here and then 6, which are the chi, what we call chi, let's say capital I from 1 to 6. So like this this group of fermions is related to the 10-dimensional sine mu. And then the new fermions we got were the sort of internal fermions that we said you can sort of relate if you want to the like 6-dimensional manifold or space that you compactify on. So the 6-dimensional space like that you'd hear about in other string theory setups where you have you're like a manifold and that's your compact internal space, the other dimensions that you don't see, blah blah blah. But I mean, I said that in a way which is, I sort of said that's a choice if you want to make that connection. But in our language, it doesn't really matter if you make that connection. All that matters is these are just degrees of freedom, which are fermions. We in the free fermionic we always choose fermions, but then you could bosonize them and make them bosonic like normal coordinates. But all that matters is these are degrees of freedom that make the conformal field theory consistent in the sense that the conformal anomaly cancels and everything's consistent. So that connection is just something that allows you to relate free fermionic models to other string model building ideas. These were both holomorphic, so W and so Y and W, and this is I, where this is again 1 to 6. And then the same thing on the anti-holomorphic as Y bar. I'll just put I, but I means 1 to 6, and W bar 1 to 6. Okay, so these are the new fermions essentially, and then we have still this group of complex fermions, phi bar, capital phi bar. I think you've been using a 1 to. So remember, we've been going to 16 because we've said these are complex. In general, we've been working with complex fermions in the gauge sector, but these are real fermions. So these are real. I'll make a note of that, real. So you've got 12 on the left, or holomorphic real fermions, and then 12 on the anti-holomorphic real fermions. And this is 16 complex fermions, which could be just written as 32 real fermions. I'll also make a note that last time I also said that we generally we will complexify these. So at the moment, this is 6 real fermions, but you can complexify them into 3 complex fermions. So, so we write them by, if we combined chi1 and 2 into like chi1 plus I, chi2 normalized is what a complex fermion, which we call chi1, 2. And we do the same with 3 and 4 and 5 and 6. We just pair them up, make a complex fermion. So there's 3 complex fermions here. Yeah, 24 real fermions here, and then 32 real or 16 complex here. Okay. Right. So now we want to do some model building. So so the simple models. Maybe I can just rub that order out just so I can start again. So this is just the sort of starting point line. This is our degrees of freedom. So simple models. This is where we're going to use knowledge that we learned before. So if you remember, the simplest model was the 1 model, right? And in 10 dimensions, this model had a number of we had to, in order to actually show these things, we had to do, we had to check the GSO projections and I mean, the 1 model, remember, gives rise to 2 sectors, 1 and NS, where NS is like 1 plus 1, just the sector where all of the fermions are aperiodic. So in 10D, I'll just remind you of the key things we found. So key thing number 1 was, let's say we had a tachyon. So tachyon, which was from the NS sector. So it was like when we had the NS sector. So this is like the NS vacuum, and we applied a single anti-holomorphic fermion. This made this state negative mass. It's like a negative mass level, but it's level matched. If you recall, it was, I think, at the minus a half mass level. So it's a tachyon, and there isn't any GSO projection that projects it. So it's in the Hilbert space. So it's in the model. So this means that the model has a tachyon, which means it's unstable, has an instability. This model isn't. You have to reformulate the model basically to make it stable, make it formulated around a true quantum vacuum, whatever. This is this just says unstable theory. Just write unstable. And then the other things about this model were we had an SO32 gauge group. So we had 16 complex fermions that give rise, these gauge fermions give rise to SO32, which were from the state psi, mu, and then 2 gauge fermions from the NS sector. Okay. And yeah, these are the gauge bosons that gave rise to SO32 in the adjoint representation we kind of mentioned last time, but maybe didn't explain it fully, but that's what the result is. So these SO32 just associated to these gauge bosons. What else? I mean, we also noticed that there certainly wasn't any supersymmetry in the model. There was no symmetry between the number of bosons and the number of fermions. In fact, in this model, at the massless level, remember, there's only 2 sectors in the model, 1 and NS. at the massless level, like, well, one, the sector one is massive, if you remember, because one has, you know, the 16 complex fermions on the gauge from the anti-holomorphic side, which meant that the anti-holomorphic mass level is above zero. So only NS was massless. And the NS sector only gives rise to bosons. So, you know, even the tachyon, which is the lower mass level, this is a boson because if you remember a fermionic, so recall like a fermionic fermion, so this is with respect to like the spectrum, like the space-time interpretation of states. The fermions will come from sectors alpha, sort of such that the boundary condition in the sector for the space-time fermion is 1. So like, for example, the vector 1 has this is true, right? You know, 1 has periodic for everything. So it's certainly periodic for psi mu. So 1 is fermionic. This will give rise to the fermions. But this, you know, NS, everything is aperiodic, so it gives rise to bosons, right? So this is the sort of condition for finding fermions, and this would be the condition for bosons, right? Like just the same thing, like alpha of psi mu, but this is equal to 0, so it's aperiodic. So all the, you know, this obviously gauge bosons are obviously bosons, but there's no fermions, there's no partners, super partners, or things that could, like fermions that could be super partners of the bosons. So this model clearly has no supersymmetry. You know, everything at the massless level is bosonic. There are only fermions from the one sector, but they're going to be massive. So each level, they're not going to really match up anyway. So that was, if you recall, what we found in 10D. Right. So maybe I'll just simplify that. So we found tachyon SO32 n equals 0. So let's contrast this to what we'll find in 4D. And I'm not going to derive this now. You can do it yourself if you want. I'm going to look at the 1S model in more detail. But in 4D, the one model, you know, we still have 2 sectors, right? Nothing's changed there. Just because you've got these extra fermions in 4D doesn't change that you can only create sectors out of the one basis vector by 1 plus 1 equals ns and 1. So these are still the same. This is still the same. And so what do we find? Well, we still have tachyonic. We're still a tachyon because we've still got the same states. So we can still act. We can still act on the NS vacuum with a. I'll just write it like that. Let's say. So you can write this state. So if you act with an anti-holomorphic oscillator on the NS vacuum, this will give you a -1/2 mass level. It's still the same as here. It's the same state, but you could also be acting, remember, with so F bar A is essentially going to be like these all of the anti-holomorphic options. You know, you've got the 12 real Y bar, W bar, but also the 5 bars. So you still have tachyon from here. Then what do we have? So instead of SO32, we'll actually get SO44. So now, because we have these extra Y bar and W bar, the gauge bosons will be like the same, but instead of phi bar, instead of only having phi bar, we have like F bar. Yeah, because there's an extra 12. So you could say this is a 12 plus 2 times 16. So really the 16 complex is 32 real. So there's 44 real fermions. Or you could say, yeah, this would be like 22 complex fermions if you try to complexify these, but in general, we'll keep them real. But really, like if you have 44 real fermions, then you can get 44 SO44. If you remember, we said that if you had sort of N, so if you recall, I'll write it and then rub it off. So N complex fermions with the same boundary condition in the basis vectors would essentially give rise to the gauge bosons like this, which would be the adjoint of SO2N. If they, yeah, so N complex boundary, N complex fermions with same BCs, so the same boundary conditions for all like basis vectors. So if you have N complex fermions with the same boundary conditions in all the basis vectors, then they will give rise to these kind of gauge bosons, which are going to give you the adjoint of SO2N as the, and that gives you that's why, for example, we get SO44 here rather than SO32 here. I'm going to just put that off, but keep that in mind. And then, okay, so N equals 0. Well, we're also going to get N equals 0 here, because nothing's changed in terms of the supersymmetry. We've still got, NS sector. So we only got bosons at the massless level, and there's no fermions to balance it out or whatever. So there's no gravitini, for example, which is usually how we define whether we have supersymmetry or not, which we'll do in a second with the 1S model. So essentially, that's the main things I sort of want to point out. You could also note that if we looked at this model a bit further, if you looked at the NS sector for 4D, there would be states like with the chi y. So before it was just psi mu, right? In 10D you just had psi mu. But you'd have sort of states like this, where you act with one of these oscillators and then have so instead of having so we know that we get the gravitational states, remember, from we have psi mu and acting with this sort of bosonic operator on the anti-holomorphic side. So the NS sector will always give rise to the gravitational state where the holomorphic oscillator is psi mu. So that's always there in all string models. We want to have the gravitational sector, which gives the graviton, etc. But here, because we've gone to 4 dimensions, we have these chi, y, and w's, so they can also act as the holomorphic oscillators. And these, well, we kind of mentioned this last time where we talked about how we chose the supercurrent, and how we chose the supercurrent would give these different gauge groups. And this was actually, our choice was SU2. So each group of these three gives an SU2, and there's 6 of them, so there's like an SU2 to the 6. So there's a sort of additional symmetry, which is on the holomorphic side. And remember, the holomorphic side, these aren't gauge fields. We only interpret these as giving rise to, well, we can interpret all of these on the anti-holomorphic side as the sort of gauge symmetry. So this is sort of new, like this is a gauge symmetry on the holomorphic side. And these coordinates are something to do with the internal space, because these are like the compact parts of these are the compact parts of the manifold, and these are the compact parts of the fermion. So this is sort of sometimes called like a horizontal symmetry, or an R symmetry. It's sort of related to having an R symmetry. But we'll we can revisit this. This is just a minor point that I'll just mention. But if we wanted to do this model in more detail, you just have to note that you get these states, for example, where in 10 dimensions you obviously just have psi mu as your only oscillator on the holomorphic side, and you could also have states. Similarly, you'd have states like where instead of acting with the bosonic operator, you'd act with the 2 gauge, or the 2 anti-holomorphic fermions. So this would also be a state in the NS sector. What do you mean exactly? So this would also be valid states in the NS sector, where instead of having the bosonic operator, we've got 2 fermionic. This would give you the massless states. I mean, these are bosons in space-time because of what we said before. So the interpretation of these is something like, these give you a representation of SU2 to the 6. This still gives you an SO44. So you have, some of these sort of, these are like the parts of the gauge bosons that, couple with this SU2 to the 6 representation on the holomorphic side. Okay. But that's not, these states, I'm not really, for now, that's not that important. We just want to talk about the main features of the model, which are what we've just said, that we still have a tachyon, we have a bigger gauge group, SO44, and we had n equals 0. Okay, that was the main sort of highlights of the one model and how it extends to 4 dimensions. Okay, now I'll look at the 1S model in 4 dimensions and sort of give a bit more detail than I did for this one model. Right, so let's keep a similar structure. So now let's do the 1S model. Okay, so we noted that the point about S in 10 dimensions, so S in 10 dimensions was just this. We just put the space-time fermion as periodic, and everything else is aperiodic. And what this did was, well, if you recall, if you had the tachyon, so we took the tachyonic sector that we wrote down before for the 1 model. If you act with the GSO projection with S, then the GSO phase, so remember that there was some condition on the GSO phases, which was that so we will always take this convention. You know, there's some constraints from modular invariance on these GSO phases. That the phase 1s is equal to 1, 1, and we'll generally choose it to be -1. And this is I mean, it doesn't actually matter how we choose this as long as it's modular invariant, and we'll still get the same results, but I'm just being concrete that this is our choice usually. So remember, to fix a model, you have to fix the basis and the GSO phases. And in this case, the only three GSO phases are sort of 1, 1 and 1s. But modular invariance means they have to be the same. And if we choose -1, for example, if we take the tachyon that we had before, so that was the NS vacuum acting on by one antiholomorphic fermion, this is projected by the GSO projection with S. So the tachyon was projected. So we showed this more explicitly last time. Tachyon projected by F. Okay. Last year I was writing the gauge. So the gauge group SO32. So it's the same because we haven't really done anything on the gauge. We haven't split up the gauge fermions if we add S. So we still have 32 complex fermions, which will give rise to SO32. But then what about supersymmetry? Well, if you remember, the sector S gave rise to, we had a gravitino. The gravitino. So this is the main point about supersymmetry for us, is whether we've got a gravitino or not. So the gravitino state of was this. So we take the sector S, and then we have the bosonic operator, and then so the sector S. This is like this is just the Raman vacuum for the sine. Okay. So this is like plus minus for the sine fermion. And so you've got something I explained it a bit like, saying this is a spin 1 because it's bosonic. This is a spin half because it's a fermion, spinorial. A spin half. And if you combine them, you can get a spin 3/2, which is a gravitino. Okay. And so this is a single gravitino. This is one gravitino because there's just a choice, plus or minus, for the sine mu. And you will either choose plus or choose minus. I mean, actually, because it's a spinner, the two components are not independent. They're CPT conjugates of each other, but this is just really one state. So it's n equals 1. Okay. So the S sector projects the tachyon, but it also gives us a gravitino, which is the sign that we have supersymmetry, and it's n equals 1 supersymmetry because there's just one of the gravitino. But also the whole spectrum, the whole set of states is supersymmetric. For every boson, you have a fermion. And that was where we see that in this sort of language by saying, right, we have the NS sector. So for example, at the massless level, We have the NS sector that gives you, the gravitational states, the gauge bosons, all the stuff we talked about. But then you have the S sector, and that gives you all the superpartners of those states from the NS sector. So, for example, the gauge bosons from the NS sector become the gaugini in the S sector. They are just, the partners, but they have spin half less. They're just the fermionic superpartners of the gauge bosons. The gauge bosons, let's say, will have spin 1, and then the gaugini will spin half. And they'll partner up and they'll form. If you wanted to, write the spectrum, you could in terms of super multiplets, and then you group together the fermions and the bosons that match up into a single representation, with respect to the supersymmetry. n=1 supersymmetry representations. And that's a general result. So the general result is, if you have a sector alpha, you can take S plus alpha, and these sort of form, I don't know how to write it exactly, but these are this would form like a super multiplet. So this would be, so let's say, okay, so how about this? So for all sectors alpha in, remember we use this symbol for the whole space, the whole vector space, all the combinations of the basis vectors. So for all sectors in the whole space of the whole vector space of the model, S plus alpha are super partners, or give super partners. You can't read that, can you? So super partners. Give F partners. Okay, that's the general result. Okay. So now that's the 10D case. So now let's look at this model in 4D. So we derived all this last few weeks ago, right? But just reviewing. So now let's do 4D. So in 4D, so the first thing is that S still projects the tachyon . Okay, so nothing really changes there. You've still got tachyon from the NS sector, and the S projection basically works the same. It has no intersection with the tachyon, and its GSO phase is fixed such that this will just be projected out of the spectrum. And then what do we have for the gauge group? Well, the gauge group is going to be SO44, right? In the same way we got SO44 for the 1 model. The 1F model doesn't really change the anti-holomorphic gauge boson states. They're still going to give SO44. So yeah, I don't need to say much more about that. But then what about the SUSY? So SUSY, right? So what happens with the SUSY? So let's do that over here. So I'm just rewriting that. So no tachyon. So SUSY in the 4D model. So let's just let's do this in a bit more detail. Right, so what do we have? So S in 4D, well, S in 4D is, we write it like this because, well, let's write it with chi 1, 2, chi 3, 4, chi 5, 6. So like I said before, we usually complexify these chi's. So this S, so S is defined, it will be, periodic boundary conditions for the both the compact and the non-compact components of the space-time spinner. Okay, so this is why it's the sine u and the chi's. So that's how you define S in 4 dimensions. Okay, and then if you want to look at the massless, we want to look at the massless states that come from the S sector, and obviously for the if you want to look at SUSY, we want to look at the gravitino or gravitini. So we have this just as we wrote in 10 dimensions, we have I write nu here, so you get confused with the mu here. So the same state, so we're taking the S vacuum, the Ramond vacuum for these periodic fermions, essentially with just the bosonic operator on the anti-holomorphic side makes this massless. So we still, this is the same as we wrote essentially in 10 dimensions, but now just, well, I'll write it here, so this vacuum means, you've got plus minus, plus minus, plus minus, plus minus for these 4 periodic fermions. So you've got sine u, chi, chi, chi. Okay. So a priori, this looks like 2 to the power of 4 possibilities, right? So each one is 2 times 2 times 2 times 2 possibilities before we've done any GSO projections. But now we have to think about what do the GSO projections do to this state. So the GSO projection with 1, what happens? Well, you've got e to the I pi. So just if you want to check back at the GSO projection, but remember you have on the left, you have this so e to the I pi is like a -1, like a to the power. So -1 to the power of the vector that you're projecting with, so which is 1 in this case, dotted with like the fermion number with the sector. So we write it like that. So f of s. And then that acts on your state. So I'll just write like the state. And then you've got the GSO phase between the sector you're projecting and the vector that's doing the projecting. But then you also have this operator, the space-time spin statistic operator, which is delta, which is just the ±1, depending on the boundary conditions of the space-time fermion in the sector that it's with respect to. So here, S, this will be -1. So this will be -1. This is like saying boson or fermion. So it's saying it's -1 because the sector S is a fermionic sector in the sense that the boundary condition for sine mu is 1, like periodic. This, I already told you that we will fix this to -1. So it has to be the same as C11. So we take this as -1. So on this side, we have an overall plus, -1 times -1, which means that this thing here So 1 dot f of s gives, this has to be even. Because that means that this is like -1 to the power of an even number to make +1. And that matches the two signs. Okay, so what that tells us actually is, because, yeah, I mean, remember that there's the oscillator here, the bosonic oscillator as well. So really this is like 1 dot, the fermion number of, the whole state, which is the bosonic operator acting on this vacuum. But the bosonic operator, it's a boson, so the fermion number is 0. So that's, really this has got two parts. It's like the oscillator part and the action on the vacuum. But the oscillator part is 0 because it's a boson. It's a bosonic operator. So the fermion number is 0. So you only have to worry about the bit where it's like the fermion number of this, the Ramond vacuum of the fermions. So this even is actually saying, well, this vacuum here, so this vacuum S, which is this psi mu chi 1 2 chi 3 4 chi 5 6, is you have to, this is sort of, we need to get an even number from here. So it's actually saying that we have like an even number of, let's say, minuses. If we have an even number of minuses out of these 4, then this will count an even number of minuses from the fermion number. Because if you remember the fermion number F of S, like what that means is the fermion number of this, and this added together. So the fermion number of plus or minus, well, the definition is that the fermion number of a plus is actually 0, and the fermion number of, probably you can't see that, the fermion number of a minus is -1. So when we say that this dot product is even, we mean that the number of minuses here is even. So what this means is we often write this, so the notation we write is like the number of states, the number of like Ramond fermions we have in the vacuum, we write like up here, and then we say the number of them that have to be minus here. So we have like 4, or we could write this as 4 even. So what this means is like 4 0 plus 4 2 plus 4 4. So what this is saying is like, there are, for there to be an even number of minuses here, you could choose all of them plus. You'd have 4 pluses. That means this one. You could choose all minuses. So minus, 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 minus. That's this one, 4 4. So I can write that here. So plus, this means like plus, 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 plus. This one, this is like minus, 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 minus. And then 4 2 is just where we say, well, we choose 2 of them, but they can be chosen like any 2. And, you can choose, so the binomial coefficient 4 of 2 is just the number of ways to choose 2 things out of 4 things. Okay. So this kind of counts the number of possibilities of this. So you've got 1, so this would be like 1 plus. The binomial coefficient of 4, choose 2, I think is 6, but you can check. So yeah, 6, so 4 factorial over, 2 factorial is 6. So it's 1 plus 6 plus 1 is 8. Yeah. So let's just kind of summarize that result. So what we have is after the one projection, it implies that this state is actually going to be restricted, so that we have what we could write as 4,0 plus 4,2 plus 4,4, like that. Yeah. Okay, so 1, that's the projection with 1. The projection with S isn't going to do anything because the projection with S sort of trivial. It'll just give you, well, it won't create any new constraints. You can check that. But generally, if you have a sector and you do the projection with itself, it shouldn't really do anything interesting. So now what do we have to do? Well, so notes. So this was a bit, we also made this note in 10 dimensions. So if we note sine mu, so if we write like the fermion, the Raman fermion vacuum for this, plus minus. So this is a space-time, this is a Weil spinner. So a Weil spinner is like a spinner with like components where you can, choose the two components. And the two components of Weil spinner, well, these are like two components. So two components not independent. So this is only something we have to think about with sine mu because it's a space-time. It's got sine mu, so it's a space-time representation. So this is with respect to like, how it acts on how it behaves in space-time. So it's a Weil spinner. So the plus and the minus are not actually independent. They're going to be actually one thing is you can get them from CPT conjugation. So if you do like, for example, Dirac theory, you see this like charge conjugation, parity in time, and overall, the Dirac equation is invariant in the CPT, as is all quantum field theories essentially. So if you flip these around, you get the two components by CPT conjugation, which means they're not independent. So what we can do is just say, well, let's fix psi mu to plus, let's say plus, and then the minus we'll just ignore and we'll just say it's CPT conjugate. So we just take the plus. So here, this 4,0, 4,2 plus 4,4, what we can write is, well, this is going to be the bosonic operator, and then if we fix this to plus, so say fix plus, we're going to have, so plus, so one way to write plus in our notation is if we just have a single plus, that's like writing 1, 0, because there's no minuses, it's just one fermion, or one, so it's just 1, 0 binomial coefficient. So this we could write as 1, 0, and we've got 4, 0, 4, 2, and 4, 4, but now we've got a 1, 0, so for the first one, That's like going to be 1, 0 times 3, 0. And then we're going to have 4, 2 has become 3, 2. And then we've got 4, 4 is 3, 3. Well, 4, 4 is only possible in the CPT conjugate, like when you've got this as minus. So we'll write that as well. So and then plus. So then I can just put like plus the CPT conjugate. Okay. Which is when psi plus. So this is psi mu. And this is the chi's. So if you look at this now, because we've split into two components, what we've done is we've got 4. So before we had 8 possibilities. So this is like 8 choices before, but because we've split up the two components of psi mu, we've essentially halved the number of choices. So if we take psi mu plus, we get half of these 8, which is the plus plus. So this is the 4 pluses. So plus plus plus. This is like plus minus minus, and then permutations of plus minus minus, like minus plus plus, minus minus plus. So there's 3 choices there. So this is like 1 plus 3. So there's 4 choices. So, and then if you look to the CPT conjugate part where you have, you take the minus for psi mu, you'd get 4 choices there, which would be like, you know, minus, like 1 minus there, and then 3, 1, and then you'd have 3, 3. So I could write it. So the CPT conjugate part would be like 1, 1. So the minus for psi mu, and then you'd have 3, 1 plus 3, 3. Okay. So there's 4 choices here and 4 choices here. They're not independent. So actually what you have is there's really 4 states here. So there's 4 gravitini. Okay. And what I've done here is completely general. Like you can always choose psi mu to be plus and then just kind of ignore the minus because you know it's there as a CPT conjugate. So it might seem like a complication, but it really makes your life easier because you can fix psi mu to plus. Or well, you could fix it to minus, but then everything would be like reversed. But just fix it to plus and everything gets halved. So you've got 4 gravitini. So you've actually got n equals 4. So n equals 4. So we've gone from a theory in 10 dimensions, which had 1 gravitino, to a theory in 4 dimensions, which has 4 gravitini. And that's kind of happened because, you know, we've split up the psi mu into compact and non-compact parts. So we have the chi's now. So there's 4 fermions, and they all have a possible Raman vacuum of plus or minus. Whereas in 10D, we only had 1. We only had psi mu. We just had to fix it plus or minus. So we went from n equals 1 to n equals 4, essentially because of that. Okay. So what time are we on? So we've got a bit longer if you want. Okay. Maybe we'll do something else. If that's all right for you. Maybe I can say something about the partition function. Right. So I mean, one other thing I could say is, I haven't talked about, like the other states in the model, the 1S model in 4 dimensions, like what's different with 10 dimensions. Um, I mean, for example, um, yeah, so for example, we said before that like there was states like this, where you have these holomorphic oscillators in the NS sector, and you can either have like the bosonic one, or you could act with two fermions on the. So these were, are the states I mentioned for the one model in 4 dimensions. If you do the S projection, so this is like these acting on both these. If you do the S projection, GSO projection, then the basically, because remember S is sine mu chi. So S has different boundary conditions for the chi's than the Y and W. So just a reminder, that's so what actually happens is only the chi's as oscillators are possible if you have the S projection, because the boundary conditions for the Y's are aperiodic. This is periodic. So when you do the GSO projection, you basically only keep the periodic part, the chi's. So these states are projected to these states. Well, let's write it like chi1, 2, chi3, 4, or chi5, 6 as the left oscillator acting on either the bosonic operator or the two fermionic anti-holomorphic oscillators. So you project out the states where the Y and the W were the oscillators, which just changes. I mean, one other thing is this: these states here. We'll come back to this, but these states here, remember, these could be the Y bar and the W bar, or the psi bar, the phi bar, sorry, or the phi bar. And what one thing we can talk about. So something that's important here would be that if these are for these states, if these are the oscillators, with chi as the other oscillator, so these states like chi with a Y bar and a W bar, these will be like scalars, because like if we have the phi bars, that they'll. I mean, this is maybe better to mention later on, but in general, like if we start building models later on, where we use the phi bars will be our gauge group. They generate like a 16-dimensional gauge group in some sense. But then the Y bars and the W bars will be like part of the internal space, the 6-dimensional compact space, etc. So this will relate to some internal space. And if we have chi and then a Y and a W on the NS, well, that's not going to be like have a gauge representation because it's not the 5 bars. It's well, yeah, that's true. So it's not going to have a representation with respect to the gauge group. It's just going to be a singlet or a single. It doesn't transform. It's a scalar. And if you have a scalar like that, it's going to it's going to be what we call a modulus, or moduli. So we'll talk about this more later, but because if you have in your spectrum scalars, massless scalars, they in general are going to be this is one of the problems with string theory, right? That you get a lot of massless scalar fields, and those scalar fields in general could have their own like vacuum expectation values, and this could makes this sort of freedom in your model that needs to be sort of stabilized, which we'll talk about later. I'm just we'll come back to this later on, but so all I wanted to just say is that there are other parts of the 1S model that I haven't mentioned here that you can check yourself if you want. For example, these states. Right. Right. So the partition function, right? We talked about before. The one I didn't mention this last term, or sorry, like a few weeks ago when we did the 10 dimensions. I mean, I gave you the definition at some point of the partition function right at the start of the lectures. But if you recall, we had a partition function which could be written as like the partition function for the bosons, like x mu. So x mu, and then the partition function for like the fermions, ZF, let's call it. The partition function for the bosons is it's not that interesting for us. The fermion part depends on like boundary conditions, so it's going to be something that changes for different models. But this is always going to be the same because you can't give different boundary conditions for like the fermions, just for the bosons. So we're talking about 10D now, so 10D. So in 10 dimensions, the partition function for the bosons is going to be like 1 over eta to the 8, eta bar to the 8, these modular forms that we talked about, eta and eta bar. The fermion part, so the interesting part is this fermion part, which depends on the two components that we said would determine a free fermionic model, which are the GSO phases and the boundary conditions. So what we just write like Z, alpha, beta, and this is going to depend on the basis vectors essentially. I think I prefer writing it like maybe like this. So what this means, we want to take product. Oops. let's put the product here. And then we've got the phases. And then so we sum over all the sectors in the model. So all the sectors in this like vector space that we called like this chi thing, or xi, whatever. Then you got the GSO phases, and then these things, the partition functions of the fermions with respect to their boundary conditions. So if you look at this, it's like a product over the fermions. So psi mu, phi bar, 1 to 16 in 10 dimensions. And then you take the product. And in general, this is going to be like theta over eta, or theta bar over eta bar, depending on if it's holomorphic or anti-holomorphic. That was the so the theta bar is what depends on the boundary conditions, and the eta just sort of goes along as like a factor. So these are going to be this partition function. This part's just going to be the product of theta functions, where you get a theta function for each fermion that's determined by its boundary conditions. So it could be 1, 1, 1, 0, 0, 1, or 0, 0. But if you have real boundary conditions, you've got 4 possibilities. So what I wanted to do, if we take probably 5 minutes, is just to do that for the 1S model. Okay. It might take 10 minutes. Right, so what do we have in the 1S model? So 1S. So 1S in 10 dimensions. Well, here we have the sum over alpha and beta, like all the sectors. So let's just write what all the sectors are. So alpha, beta are going to be like in the set of the sectors, which will be sort of the NS, which I write 0, 0 vector. Then you've got like 1. Then you've got like S. Then you've got like, I guess 1 plus F. And that's it. Yeah. So you've got 4 sectors. So this sum here is going to sum over, all the possibilities of these 4 sectors. So I think there's going to be 4 times 4, like 16 terms. So ZF is going to be essentially like C, like 0, 0, Z, 0, 0, plus like C, like, I guess 0, 1, let's say, Z, 0, 1, plus, and then etc. And you should have 16 terms. So it looks like it'd be quite long, but there's a way to simplify it. So simplify. We simplify it by noting that theta 1, 1. So if you have the theta or theta bar, so remember this, so this like this this partition function for like the 0 and 1 sector, is really like a product over all the fermions, which is a product over the theta function for each fermion, given by its boundary conditions in the two sectors that you're looking at. So for example, 0 and 1, well, 0, all of them are 0. All the fermions are aperiodic. In 1, they're all periodic. So this would actually be, theta, theta 0, 1. And then there would be an eta divided by eta, but it doesn't really matter. And this would be to the power of 4 because there's really 4 complex components to the psi mu. And then on the other side, you've got theta bar, and it'd be 0, 1 for each of the gauge fermions. So it would be theta bar to the 16. And then, yeah, the etas you could just factorize out. So eta to the 4, eta bar to the 16. So this would be the partition function for this one, for example, multiplied by the phase, 0, 1, the GSO phase. So that's what that term would be. So really you would have like 16 terms like this. Like that would have a phase multiplied by this, like some theta function, maybe with different boundary conditions here. But there would be 4 on the holomorphic and 16 on the antiholomorphic theta functions. But we can simplify any of those where the theta function or the theta bar has 1, 1. Because if you have 2 Ramond boundary conditions, the partition function actually vanishes, it's 0. Sometimes it's helpful to keep the 1, 1 theta functions in the partition function just so you can check modular invariance. But they are 0, so we can simplify just by deleting all of the ones where there's a 1, 1. So what that means is like any of these 16 things where there's in the two sectors, so when you take these two sectors, so for example, S and 1 have common periodic fermions, right? Because psi mu is periodic in S and 1. So is 10 dimensions. Psi mu is periodic in both, right? So that means that the theta function for psi mu is going to be 1, 1. So if you have like the term, so here if we just put in this term 1s z1s, then there's going to be a theta 1, 1 to the 4 from the psi mu. So this is 0. This vanishes. So any combinations where you have some periodic fermions that are common, like they're in both of these two sectors. So like 1 and S, 1 and 1, like S and S, 1 plus S and 1. Maybe I'm doing this quickly, but just think for a minute. Which of these combinations of two sectors have common periodic fermions? So 1 plus S has got periodic fermions for the gauge part, right? So 1 plus S, remember, you got 1, so they're all periodic. You add S, so the psi mu is not periodic anymore. It's aperiodic. So only the gauge fermions are periodic. With 1, everything's periodic. So there's periodic. There's the gauge are periodic in both. the phi bar. So that means that the term, so also this one, so 1 plus s with 1, that's also 0. So any terms like that where you have common periodic fermions are going to be 0. So then we can simplify the partition function. So and I mean, basically, I guess I should probably finish now. But what you'll do, so there's only, I think, 9 out of 16 non-zero. Okay. You can try and just check that. So I'll just put check. And the actual results, so Z, F for the 1S model is, we can write it as, well, we always have the eta to the 4 and eta bar to the 16. So every term is going to come with an eta, and you can just factorize it out. And then you can write the partition function for the sine mu. So the sine mu is always going to have some kind of theta function to the 4, and you get oh yeah, so I should say here as well that remember for 1s, you know, C1s is -1, and we chose C11 equals -1 as well. So we can fix all the GSO phases. And then they just yeah, just plus or minus ones in here. So we don't have to write the phases. You can check. You get the same minuses and pluses. So what do we have? We have minus. You could chalk. So we've got this is for the sine mu. We've got these. We're going to have the theta functions when it's like 0, 0, 1, 0, or 0, 1, because the 1, 1 will be 0. And the order there is make sure I'm consistent with everything. Here we go. So this is a 0, 1 with a plus sign, and then the other two like 1, 0. So 1, 0 and 0, 0, they come with a minus sign, so you can swap them over. So that's the part for the sine mu, the holomorphic part. And then the other part is going to come with powers of 16 because it's the gauge part, and all the 16 fermions have the same boundary conditions. So they're going to group together into the same theta functions. and you get is it plus plus? Yeah. So you get theta. Yeah, you just get like theta to the 16, theta bar, plus each one plus together. So maybe you can't see this very well. And then theta bar 0, 0. Okay. So the gauge parts all come with a plus. But the gauge part's not so important because what I'm going to tell you is that this thing here, so this is the sort of the conclusion I wanted to come to. So this part here for the sine mu, so you've got these three theta functions all to the power of 4. This is actually this thing here, this three theta functions, each to the power of 4, like this. This is Jacobi identity. What's called the Jacobi identity. So this is just a result from from mathematics in the theory of modular forms. The Jacobi identity. These theta functions, like this minus this minus this, with all the powers of 4, is 0. Okay, and that's important because that means that the partition function for the 1s model is 0, and actually we knew this is what we should have get because the model has supersymmetry. So actually, the whole thing, so you can kind of connect all these things together. So if you have supersymmetry in a partition function, actually the fermions contribute the opposite of the bosons. So they should contribute the same, but with a minus sign. So what's happening here is that this Jacobi identity is somehow in the partition function, what basically tells you that in terms of the theta functions, that's how you see that the bosons and the fermions cancel out. So somehow there's a connection between the Jacobi identity and supersymmetry. Like the supersymmetry, the cancellation is embodied by this like Jacobi identity in some sense. So that's sort of an interesting result that shows the connections between modular forms and the modular symmetry. Because remember, modular forms arose because our theory had to obey modular symmetry, right? It was like we had these S and T transformations. So we had to use our partition function had to be modular invariant, which meant it had to be built out of things that transform well under modular transformations, such as the theta functions. So then, in some sense, you can say that modular symmetry and supersymmetry, or like in terms of modular symmetry and modular functions, this is how you embody supersymmetry. Okay, that's all I wanted to say today. Sorry it went on a bit. Any questions?
No, thanks, Ben. Thank you very much.
All right, thanks. Next week we start doing more realistic models where we add extra basis vectors, and then we start creating something which gives you some phenomenology, like particle physics features. Okay.
Okay.
So yeah, I imagine there was quite a lot in the lecture, but if you read through the notes and still have questions, just come and ask me. Okay.
Yeah. Thank
Right.
you.
See you next
Bye.
week, hopefully.
See
Right.
you.
Bye.
Bye.